So welcome back to our latest lecture session, right? So we have been discussing the practical applications of acid bases, and how to look at employing or deploying Vimitech to be able to make your life easier, right? And I believe in the last lecture session we discussed problems with respect to mixing two solutions of different characteristics, and we saw that we need to balance conservative quantities, right? For example, when I think the example we looked at was looking at solution of pH 6 and pH 8, and if you mix them together, what would be the pH, given that you have different alkalinities present and so on. So you can't obviously just take the average, neither can you just take the average of H plus concentration. So you need to take the you need to look at the total component balance or balance on conservative quantities. So component balance is something that we are aware of, and conservative quantities are alkalinity, acidity, and so on, right? So today we are going to move on to probably the last aspect with respect to acids and bases. So here again we are going to consider a mixing problem. So first we are going to discuss the theoretical basis for this, or how to solve or approach these kinds of scenarios, and then we are going to look at a practical example and how to use Vimitech or solve by hand to analyze that particular situation, let's say, right? So let's move further. And so the aspect that we are going to look at is when the theoretical definition of alkalinity is not consistent with the measured alkalinity, right? So and when is this the case, right? And as we know, alkalinity, the theoretical definition, what is that? I think what are the bases here? In the carbonate system, HCO3 minus plus 2 times CO3 2 minus plus OH minus H plus, right? So this is considering when we have only the carbonate system, and that's what we look at with respect to the theoretical definition of alkalinity anyway, right? So obviously when would this particular definition of alkalinity not be consistent with the measured alkalinity, and how do we measure this particular alkalinity? In your lab, how do you do so? So I think we looked at a titration endpoint, or we consider a titration endpoint of 4.5 as mandated by the standard methods, right? And then we take an acid of known concentration and we titrate until we reach that particular endpoint, pH 4.5, and we calculate the amount of acid, right, or equivalent amount of acid that we had to consume, or the solution consumed, before reaching that 4.5. So obviously if only the carbonate system was predominant, this particular theoretical definition would more or less be similar to what you would calculate or measure practically. But when would that not be consistent? So we looked at this case, so let's not go into it in great detail, but let's look at this case when we also have the species of PO4 phosphate, let's say, HPO4 2 minus, right, H2PO4 minus, and H3PO4, let's say, right. So let's say when you have the phosphate acid base or conjugate acid base species in your particular solution too, then they are going to obviously interfere with your particular practical measurement, because let's say depending on the pH, HPO4 minus or H2PO4 minus, and what is it now, PO4 3 minus 2 can interfere with your particular measurement. Why is that? They can consume the proton, right? For example, H2PO4 minus can consume 1 proton depending on your particular what is it now, pH, right? And HPO4 2 minus 2 and so on, right? Again, we looked at how to calculate that based on the reference we take, and the reference should be such that its pKa is nearer to the 4.5 value, and I think the reference we took was H2PO4 minus, if I am not wrong, the last time. Anyway, we are not going to discuss this again, but we are going to look at the applications here, let's see. So again here let's understand that if I write down the particular equation in this case, the total alkalinity will be equal to alkalinity due to the carbonate species and alkalinity due to the non-carbonate species, right. So that is what we are trying to understand here. So what are the contributing species here? And they are this, and what would that be? Alpha 1 plus 2 alpha 2 into CO3 total, right, plus alkalinity due to the non-carbonate species, right. So this is the key aspect that you need to understand, that we are going to specify alkalinity due to carbonate and non-carbonate species independently, And from our understanding of alkalinity, we know that alkalinity due to the carbonate species would be equal to HCO3 minus plus 2CO3 minus, and which we are representing obviously as alpha 1 plus 2 alpha 2 times CO3 total using the ionization fractions, right. So again, once we have this particular case, so how do we go further, let's see, right. So let's say we consider two cases. So we will look at the example later on in greater detail. So initially let's say we have pH and we have alkalinity, total alkalinity, and let's say we also have PO4 total, so which I will approximate by or use the variable x to approximate it, I guess, right. So instead of PO4 total, I am having representing it as x total. So I have pH, alkalinity total and x total. So let's say how can I calculate H total or CO3 total now? So either by hand or by Vmintek, let's say, right. So we will look at the fundamental basis here. So again, as we just discussed, we need to identify the two aspects independently. What are they? The carbonate alkalinity and the non-carbonate alkalinity, right. So how can we do this? Let's say so for example, let's say this is pH at pH 1 initially, right, and after your titration, what do you know that the pH is going to be? The pH 2 is going to be equal to 4.5, right. This is from your practical measurement, the standard method value, right. So what is your endpoint for alkalinity measurement now? You add enough acid such that the pH falls down to 4.5, right. That's how you end up measuring the alkalinity. So let's say this is the key that we are going to look at. So we are going to measure, let's say pH 1 is for example 7, let's say initial pH is 7. So I am going to use Vmintek to measure the H total, right, required to bring down the pH from 7 to 4.5, as in when would the pH fall from 7 to 4.5? When I add an acid, right, or H total increases, right. So I am going to look at the delta H total, right, and what will that give me an idea about? That delta H total is nothing but going to be the case of alkalinity due to the non-carbonate species, right, and when is that the case? When I only enter pH and X total, right. So this is the key here. Let us just look at what we are up to. So I want to be able to calculate alkalinity due to the non-carbonate species, right. So I am going to consider the case where I have no carbonate in the system, and I am going to use Vmintek to approximate that. And how can I measure that now? You know that practically, right, we measure it by adding enough acid such that the pH falls down to 4.5, which is our endpoint for alkalinity titrations, yes. So even here I am going to try to approximate that. So here for a practical, what do you say, for an example, I am assuming that the pH is initially 7. So let us say I am going to use Vmintek to mimic and calculate the amount of acid required to bring down the pH from 7 to 4.5, right. So that is what we are talking about, how much acid is required, to bring down the pH from 7 to 4.5, right, and I can look at that with respect to delta H total, right. And as we know that if there is no carbonate system present, it will be equal to the alkalinity due to the non-carbonate species. So thus when inputting the relevant variables in Vmintek, what do we need to input? Only the pH and X total, certainly not alkalinity, because alkalinity in Vmintek only considers the carbonate system, right. So Vmintek, right, when you look at alkalinity, what does it consider? It considers that the system is predominated by the carbonate species, right. So we are going to try to mimic the case where we add enough acid to bring down the particular pH to 4.5 and calculate the amount of acid required, right. So from that I can calculate what is it now? The alkalinity due to the non-carbonate species, and I know, let us say from my initial case, alkalinity due to the total alkalinity. So alkalinity total minus alkalinity due to the non-carbonate species will give me the alkalinity due to the carbonate species. This is something I can calculate, right. So then I can either calculate by hand or by Vmintek the other total components. And how can I calculate it by hand? We just looked at this in the previous slide. What is alkalinity due to the carbonate species? It is alpha 1 plus 2 alpha 2 times CO3 total, right. So this is a known value which you are calculating out here, right, and alpha 1 and alpha 2 are fixed for the carbonate system for a particular pH, and so you can end up calculating CO3 total, right. And how do I do that in Vmintek, let us say? So now I can plug in pH, alkalinity due to the carbonate species, that is what I can calculate, right, and then X total, right. And from this, plugging this in, what can I calculate? I can calculate H total and CO3 total. Again, people might ask, why can't you just plug in alkalinity due to the total, alkalinity total here, right? Well, because Tech only considers carbonate species when it calculates alkalinity. So, you are going to end up with an erroneous value, right. So, let us look at a particular example. So, I believe we are going to look at an example with respect to anaerobic digester, right. So, anaerobic digester, I think people have enough background in that particular aspect, so I am not going to go into that in detail. Yes, let us look at where we are. So, let us go through this particular question once. So, looks like 2000 milligram per liters as CaCO3, right, and that is the alkalinity, I believe, right, and we have volatile acids as 500 milligram per liter as acetic acid, and this is alkalinity total, right. Assume that all the volatile acids can be considered to behave like acetic acid, right. So, obviously, you are going to have formation of volatile acids in your particular anaerobic digester, and so here we are going to consider that all these volatile acids are going to behave as acetic acid, let us say, okay, that is a valid assumption here. And so, obviously, we are this is what we just talked about, right, that some estate will be measured as alkalinity during the alkalinity titration. So, the key is that the theoretical definition of alkalinity is not valid, right. So, here what do we have here, please? We have that the alkalinity total is equal to 2000 milligram per liter as CaCO3, and volatile acids in the form of equivalent to 500 milligram per liter as acetic acid, right. And then obviously, we are, so again you have in your anaerobic digester certain alkalinity total, right, and you also have volatile acids being formed which are equivalent to, let us say, 500 milligram per liter of acetic acid. And I believe the first aspect of this question looks for the fundamentals. What are they? The total concentration of carbonate and hydrogen ion, as in what is CO3 total and what is H total, right. So, again this is a practical application, but we obviously need to know the total components to be able to calculate any other variables, right. So, the first aspect or key aspect is to be able to approximate what is the total carbonate concentration and also the total H total, right. So, how do we go about this? We are going to obviously look at what we just discussed earlier, right. So, let us move on. So, we have 2000 milligram per liter as CaCO3, right, and that is our alkalinity total. And as we know, alkalinity total has two components. Why is that? Because we have acetic acid, let us say, right, CH3COOH initial, and what was that equal to? I think it is 500 milligram per liter. Let me just confirm that, right, that is 500 milligrams of acetic acid per liter of the solution, right. And here, as we know, alkalinity total, and the contribution is going to be due to alkalinity due to the carbonate species and also alkalinity due to the non-carbonate species here. So, there are non-carbonate species, what are they here? Obviously, right, you have HAC and AC minus acetic acid, right, HAC and the acetate ion. Yes, we have these two particular variables that are going to affect your non-carbonate alkalinity. So, the first key aspect, as we discussed earlier, was to be able to come up with calculating alkalinity due to the non-carbonate species, right. So, how do I do so, right? I am going to mimic the particular case. So, I am going to use Tech. So, what is the initial pH here? Do we have an initial pH here? I believe it should be pH 7. So, let us plug that down. So, the pH 7, right, and total alkalinity was 2000 milligram per liter. So, looks like I missed putting that in the question. So, we have pH of 7, right, alkalinity total, and thus. So, how can I calculate or end up calculating alkalinity due to the non-carbonate species? So, again, as we discussed earlier, we are going to use Tech to calculate the amount of acid required to bring down the pH from the current value to the alkalinity endpoint, titration endpoint. What is that? 4.5, right. So, how do we do that? Let us go through, I guess, right. So, let us switch over to Tech, and obviously, what do I have? I have acetic acid, right. I need to plug that in. So, it is an organic compound. So, I am going to use that here, show organic compounds, yes, and acetic acid or acetate. So, before I go through, I guess here the units are in molal. Okay, I do have milligram per liter units too. So, I guess I can use that, or if not, I can obviously, let us calculate the concentration in molar units, right. So, CH3COOH the concentration is 500 milligram per liter. So molecular weight, what is that going to be? 2 carbon, 2 into 12 plus 1, 2, 3, 4, 4 hydrogen plus 2 oxygen, right? So hopefully dividing this 500 by this, I am going to end up with a concentration in millimolal, right? So that's going to make my concentration in millimolal. So we can get that done with Vimintek, I guess. So let me open up Vimintek later on. But for now I am going to use acetate as in the units of milligram per liter, right? And that's going to be equal to, anyway, I think it's better that I calculate the concentration. So let's see how this is going to be, I guess. So let's look at what this molecular weight of acetic acid is. So that's 2 12s 24 plus 4 and 32, right? So that's 60 grams per mole, and so we need to calculate what is it now, 500 by 60, and that I am told is coming out to be 8.33 millimolar, right? So let's just plug this in so that we can switch over seamlessly to Vimintek later on. So HAC naught is equal to 8.33 millimolar units, right? So let's say H total is also going to be equal to HAC naught, right? That's going to be equal to 8.33 millimolar, or rather I am not going to look at this right now, right, because I am going to specify pH. I don't need to specify this now. Anyway, acetate total is going to be equal to 8.33 millimolar, right? So what are we going to do now? We are going to specify pH equal to 7 and acetate total equal to 8.33 millimolar, and we are going to end up calculating H total, and then we are going to specify pH equal to 4.5, which is our endpoint, and keep acetate total the same, 8.33 millimolar, and now I am going to get a new H total 2, right, H total 1. So what is delta H total? This is going to be a higher value, is it? I am going to add an acid, so H total 2 minus H total 1. So what is this now? How can the pH go from pH 7 to pH 4.5? Only when you add an acid, right? Add acid. That's when the pH is going to fall down, and the equivalent amount of acid is going to be nothing but equal to the alkalinate due to the non-carbonate species, which is acetic acid here. So that's how we are going to end up calculating our alkalinity due to the non-carbonate species, right? So let's plug this in first and calculate H total here. So pH 7 and acetate total of 8.33 millimolar, right? So let's switch to Vimintek here, and we are going to have now millimolar units. Hopefully we have that, yes. So we now need to go to the key 8.33. I'll add that to the list, and as we know pH is fixed at 7, okay. So view edit list, just to be on the safer side, back to main menu and run Mintek. Okay, so now we should calculate H total. So that's going to be equal to what now? How do I calculate H total, please? How do I calculate H total? H total, as we know, is nothing but H plus minus OH minus, right? And what else here? So we have H plus and OH, pardon me, AC minus here. And what are our species? They are AC minus, HAC, H plus and OH minus. So what is the contribution here? So it's 1 and 0, 1 and 1, H plus is 1 and minus 1, and right, and this is nothing but what is the recipe species? HAC naught that we looked at earlier, right? So anyway, we don't need to plug this in now because we are fixing the pH at 7, but anyhow, H total is equal to H plus, which we just plugged in here, OH minus minus OH minus, which we plugged in, and plus HAC, right? So this is what I was trying to elaborate here. So we need to use Excel now to be able to calculate this particular set of variables, or HT1, right? So let's first go back to Vimintek output, right? So let's say print to Excel, and now I need to be able to calculate equal to H plus concentration is this minus OH minus plus HAC, and that is going to be equal to 4.4122 into 10 power minus 5 molal, right. So, let us go back to this particular case and plug that in. So, just we can remind ourselves later on. So, right, what did we just get, please? 4.412 into 10 power minus 5. It is 4.412 into 10 power minus 5 molal units, right. So, this is HT1. Now, I need to calculate HT2, and what is the case when the pH is 4.5, but obviously acetate total is the same as what we had earlier. I think we had 8.33 into 10 power minus 3 molar units, right. So, now let us look at the second case. So, now I am going to change the pH such that it is going to be at 4.5. So, where do you have this 4.5, right. So, I am going to view it at the list, okay, seems fine, and I gave the units here, and now I am going to end up with running Vimintic, and again let us print to Excel and look at the new set of values here. So, again I need to calculate H total, that is equal to H plus acetate HAC acetic acid minus OH minus, and that is going to be equal to 5.31 into 10 power minus 3, right. So, let us plug that in somewhere here. H total 2 is equal to 5.31 into 10 power minus 3. Let us just see if we are on the right track here, not right track, pardon me. Let us just look at our value. This was the previous value, and what is the current value here? Okay, 5.3 into 10 power minus 3, right. So, now we need to get the difference of these two values. So, let us do that right here, I guess. Anyway, so that is going to be equal to this particular value minus, and what was the value from the previous case, please? H total 1, that was equal to 4.412 E minus 5, right. 4.412 E minus 5. 4.412 capital E minus 5 and enter, and so we end up with a value of 5.266 into 10 power minus 3. So, let us plug that down here. So, H total or delta H total, which is equal to H total 2, right, minus H total 1 is equal to, what was it equal to, please? 5.266 into 10 power minus 3, right. So, again how did this particular pH from 7 to fall down to pH to 4.5? Only when you increase or add an acid. So, that is why you see that your H total is obviously increasing, right. So, what are we trying to do here? We are trying to mimic the case when we add an acid to bring down the mimic your titration case when you are bring down the pH from 7 to your endpoint, which is 4.5. So, by calculating the difference in the H total, you can calculate the equivalent amount of acid added, right. And what is that particular case equal to? Not particular case, that number equal to, that is nothing but equal to the amount of alkalinity due to the non-carbonate species, right. So, that is equal to the alkalinity due to the non-carbonate species, right. So, obviously, we need to now calculate alkalinity due to the carbonate species, and that is equal to alkalinity total minus alkalinity due to the non-carbonate species, right. So, how do I get that here now? So, where is our alkalinity total? I think we had alkalinity total as 2000 milligram per liter as CaCO3, right. So, let us change the units here. So, alkalinity total was equal to 2000 milligram per liter as CaCO3, right, and we know that the equivalents, I guess 50 gram per equivalent for CaCO3, right. So, we are going to have to divide that here. So, the relevant units are going to be 2000 into 10 power minus 3 by 50 equivalents per liter. So, that is going to be equal to 20 by 5 would be 4, right. So, 40 into 10 power minus 3 equivalents per liter. So, right, hopefully I am on the right track, and so this is nothing but 0.04 minus alkalinity due to the non-carbonate, and that was equal to 5.266 into 10 power minus 3. So, I am just going to subtract 40 minus 5.266 in Excel, right. So, let me switch to Excel here. So, that is equal to 40 minus 5.266 and enter, that is 34.734. So, that is going to be equal to 34.734 into 10 power minus 3, right. Again obviously equivalents per liter units, yes. So, what is this now? This is the alkalinity due to the carbonate species. So, let us move on to the next case. So, now what are we trying to find? If you remember the question, we were asked to find HCO3 total and H total. So, by hand how can you do this? Let us say you know that alkalinity due to the carbonate species is due to HCO3 minus and CO3 2 minus 2 times CO3 2 minus, which is nothing but alpha 1 plus 2 alpha 2 into CO3 total. So, I now have the alkalinity due to the carbonate species, and that is nothing but 34.734 into 34.734 into 10 power minus 3. So, I can look up the values for alpha 1 and alpha 2 at pH 7, right, which was our initial case, alpha 1 and alpha 2 at pH 7. I can plug them in and I can calculate CO3 total, right. And then again you know the relevant speciation, so I can plug in the values for H total or in the alkalinity equation, let us say, and then I can end up calculating the H total too. So, again that is by hand. So, let us see how we can do that by VMinTech. So, obviously in VMinTech what am I going to do, right. We are obviously going to have pH 7, right. I am going to plug in alkalinity, but alkalinity I am going to plug in as equivalent to the alkalinity due to the carbonate species only. Why is that? VMinTech can only consider alkalinity as the alkalinity due to carbonate species, right. So, and what else can I plug in? I can also plug in the estate total, right. And so, once I plug this in, I should get the relevant output, and from the output I can calculate CO3 total and H total, which we are going to look at now. So, let us see where we are up to now, right. So, let us close the different Excel sheets. Okay, I am going back to VMinTech, back to input menu. So, now the pH is the initial value. What was that, please? That, as we knew, was at 7. So, pH is at 7, and view edit list, what else? So, estate is still 8.33 millimolar, right, but what else do I need to plug in? Let us go back to our particular sheet. We already have estate total, we have pH 7. We need to plug in the alkalinity as we just calculate our alkalinity, that is due to the carbonate species, that is 34.734 into 10 power minus 3, right. So, we need to plug that in here, and let us go back to here, and how do we do so? Parameters, specify alkalinity, and they are equivalents per liter. So, I will choose milli equivalents per liter, let us say, and 34.734, right, 34.734, yes, and I am going to say OK and run VMinTech, and I have the relevant what do we say, aqueous species concentration at equilibrium. So, I am going to print that to Excel, and I have the relevant cases here. So, first let me try to calculate what is it now, CO3 total. So, that is going to be equal to CO3 2 minus plus HCO3 minus, pardon me, I think I made an error here, I need to go back, right, and now plus HCO3 minus plus H2CO3 and enter. And so, I now have my value for CO3 total, right, and next I need to calculate H total. So, here I need to be relatively careful. So, I am going to first work it out in VMinTech here. H total, what are the species here? We know that they are H2CO3, HCO3 minus, CO3 2 minus, HAC, AC minus, H plus and OH minus, right. So, this H plus, what is the contribution 2 here, and obviously AC minus and CO3 2 minus, which I am not going to plug in here, right. So, anyway, or for the sake of ease, why not do that too, 2 at 0 and 1, here it is 1 0 1 0 0 and 1. How many H plus for HAC? 1. How many AC minus for HAC? 1 and 0, and again this is 0 1 0, and here it is 1 and minus 1 0 0. So, how do I calculate H plus? It is nothing but this, or H total, pardon me, it is nothing but this component balance. So, 2 times H2CO3 plus 1 times HCO3 minus plus HAC plus H plus minus OH minus. So, let us plug this in into our Excel sheet. So, let us see where we are here. So, that is going to be equal to 2 times H2CO3, right, plus 1 times HCO3 minus, right, and what else did we have, plus HAC, and where is HAC, plus HAC, right, plus H plus minus OH minus, right, and where is OH minus here, and we now have our CO3 total and H total. So, let us just write this down so that we can solve the next parts of the question, and we have CO3 total equal to 0.0414, and let me write that down here. CO3 total is equal to 0.0414, and what's H total equal to? 0.0482, let us say 0.0482, right. Again, so let us just review our approach and end today's session and continue the parts B, C and D in the next session, but let us just review what we are up to. So, again because theoretical alkalinity is not the same as measured alkalinity in this case. Why is that? You have estate, right, the anaerobic digester, you have estate formation. So, thus you can't use that particular 2000 milligram per liter in the relevant equations and plug that in and go through. So, how did I simplify this? As we divided total alkalinity into carbonate species alkalinity and alkalinity due to the non-carbonate species, and first we had to calculate alkalinity due to the non-carbonate species. How did we do that? By using Wiemann-Tech to take a shortcut, right. How did we do so? So, we said pH 7 and estate total, we calculate the H total required, and again pH 4.5, which is our endpoint for alkalinity, and estate total. In Wiemann-Tech we calculate another H total. So, the difference between these two H totals, what does that give us? It gives us the amount of acid added to bring down the pH from 7 to 4.5, given that the total estate concentration is, what is it now, 8.33 into 10 power minus 3 millimole, right. So, that is what we had. We had pH 7 and estate total equal to 8.33 millimole. So, if I want to calculate alkalinity due to the non-carbonate species, how do I do so? I need to titrate. So, I looked at this particular case, I calculated H total 1, calculated H total 2, and what is the difference here? That is nothing but the amount of acid that you are adding to the system, right, acid equivalent, right, and what is that equal to? Obviously, alkalinity due to the non-carbonate species. So, once we calculate this non-carbonate species alkalinity due to the non-carbonate species, we can then calculate alkalinity due to the carbonate species, and then we just used Wiemann-Tech, or how to use how to solve the situation or scenario by hand too, right, where alkalinity due to the carbonate species is equal to alpha 1 plus 2 times alpha 2 into CO3 total. So, you can either use hand or simplify and save time by looking at Wiemann-Tech. So, with that I will end today's session, and we will look at the other 3 or 4 parts of the question in the next class, and thank you.